Welcome to the stream. Hello. Welcome Burning Star. Welcome Sue. Hello. Welcome Nick Works. Welcome Lucas. Ohio. Welcome Powerful. Welcome Dragon. Welcome Otoshigami X1. Hello. Hello. Are you guys excited? Are you guys ready for the fearless concurrency in Rust? Are you ready to unleash some mutex and have thread running around? Are you ready to start chapter 16? Psycho? Is that Psycho? Komukstawa? Komutexwa? Komutexwa? Oh my gosh. Is that really a thing? Or did you just create it? Komutexwa? Let's go. Let's go take a mutex and let the thread running. Alright, let's do this. What is concurrent programming? What the heck is that? I heard it's a big thing in Java. I mean, I've done some of it, not in my job. I remember it's always treated as the troublesome part because like things run together, deadlocks and stuff. Thread just goes dead because things are tangled together. Welcome, Last Meow. What project did you finish? Thank you, Eric. Yeah, so it's the world of chaos, concurrent programming. Let's go. Handling concurrent programming safely and efficiently is another Rust major goal. So what is concurrent programming? It is different parts of a program execute independently, and parallel programming is different parts of the program execute at the same time. So heck, there are different things. Concurrent programming is different parts of a single program execute independently. But the parallel programming is different parts of program execute at the same time. So the difference is the similarity is different parts of a program. And in concurrent programming, it execute independently. And in parallel programming, they execute at the same time. And it's related to the ones of multiple processors. Epton, welcome, hello. Historically, programming in this context has been difficult and error-prone. Rust hopes to change that. Okay, so let's see how Rust makes concurrent programming easy. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problem were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage the memory safety and concurrency problems. So with the ownership and type system, it can help both the memory safety and concurrency problem. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. So you can detect concurrency error before running it. Therefore, rather than making you spend a lot of time trying to reproduce the exact circumstances of a run or of a under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. Okay, so Ross will tell us the problem ahead. And as a result, you can fix your code while you're working on it rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Oh, that's why it's Fearless Concurrency, because you can debug it when you're working on it, not when you release it to the public. Fearless Concurrency allows you to write code that is free of subtle bugs and is easy to refactor without introducing new bugs. Okay. Oh, so we say things are concurrent, but we are actually saying things are concurrent or parallel. Okay, that's just language usage. Welcome, Lloyd. Many languages are dogmatic about solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for message passing concurrency, but has only obscure ways to share state between threads. Supporting only a subset of possible solutions is a reasonable strategy for higher level languages, because a higher level language promises benefits from giving up some control to gain abstractions. However, lower level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Okay, so in this chapter, we're going to cover how to create threads to run multiple pieces of code at the same time, and message passing concurrency, where channels send a message between the threads, so threads can communicate. We have shared state concurrency, where multiple threads have access to some piece of data, and the sync and send traits, which extends Rust concurrency guarantees to user-defined types, as well as types provided by standard library. Okay, let's go. Welcome, Mr. Lucas. And welcome, Boftia. Hello. Using threads to run code simultaneously. Okay, we're going to create threads. This is a frequently asked question in interview. What is a process? In most current operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you can also have independent parts that run simultaneously. The features that run these independent parts are called threads. Splitting the computation in your program into multiple threads can improve your performance because program does multiple tasks at the same time, but also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. This can lead to problems such as race condition, deadlocks, and bugs. So the problems are caused by we don't know the order that the threads are being run. And those problems are race condition, where threads are accessing data or resources in an inconsistent order, and deadlocks, where two threads are waiting for each other to finish using a resource the other thread has, preventing both threads from continuing. And bugs that happen only in certain situations and are hard to reproduce and fix reliably. Those bugs are really scary. The ones that it's good that you constantly produce a bug, but if the bug is not reliable, it just appears sometimes. Those are the hardest bugs to fix. So Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running in a single thread. Okay, so you're saying multi-thread context is just harder. It's harder. Programming languages implement threads in a few different ways. Most operating systems provide an API for creating new threads. This model, where a language calls the operating system API to create threads, is sometimes called one-to-one, meaning one operating system thread per language thread. What? I've never heard of this. One operating system thread per language thread. So is Rust one-to-one? One-on-one? Many programming languages provide their own special implementation of threads. Programming language provided threads are known as green threads. They have colors? And language that use these green threads will execute them in the context of a different number of operating system threads. I really need to take an OS class because I've never heard any of this. So there's a one-to-one model and an M2M model. With colored, the threads are green. For this reason, the green threaded model is called M2M model, because the green threads will execute them in the context of a different number of operating system threads. There are M green threads per N operating system threads, where M and N are not necessarily the same number. Okay, so we're matching language thread with the operating system thread. And one-to-one means one operating system thread per language thread. And M2N is M green threads per N operating system thread. The Rust thread is one-to-one. Go-routine in Golang is green thread. Oh, so they're actually pretty different. We won't learn it in an OS class. Green threads are pretty cool. Why? Do they reduce system load? There's also another mapping from OS thread to CPU thread, and the final mapping from CPU thread to CPU core. I want to see it in a diagram. What is this? What is this? Each model has its own advantage and trade-offs, and trade-off most important to Rust is runtime support. Runtime is a confusing term and can have different meanings, okay? So what do we mean by runtime here? We mean code that is included by the language in every binary. So runtime is the code that's included by the language in every binary. This code can be large or small, depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially, when people say a language has no runtime, they mean small runtime. Smaller runtimes have fewer features, but have the advantage of resulting in smaller binaries, which make it easier to combine the language with other languages in more contexts. Although many languages are okay with increasing the runtime size in exchange for more features. Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. So Rust wants to have very little runtime. And it wants to call into C to maintain performance. Learning about OS on a technical would be useful knowledge to me. I think I want to learn OS. I don't know where to start though. String threads are a lot less demanding, so you can just kind of start 1000 without issue. They don't run in parallel though. You need OS thread for that. Oh, they're just like Kusa. They're just like grass. You can have 1000 of them, no issue. So the one-on-one thread. The one-on-one threads, there's a limit on how many we can have. What? Treat you like a keyboard? No! Welcome, super sexy, boing boing big opine nickel mimi on Yanchang. Hello. In the end, it's all a ploy to coordinate code from different places to use as much CPU time as possible. Is this like people with optimization skill? They will do that in their daily job? They want to optimize the CPU usage? Hello, Batami, welcome. First threads usually have to use asynchronous I/O. Rust has some async features too. And the concept of tasks in async Rust are similar to green threads. Well, I think we are going to learn async in the first section. So maybe we'll get to it. Ole. Welcome, Frank. Where were we? We talk about runtime. And we're saying Rust wants to have very little runtime. The green threading M2M model requires a larger language runtime to manage threads. As such, the Rust standard library only provides an implementation of one-to-one threading. Because Rust is such a low-level language, there are crates that implement M2M threading if you would rather trade overhead for aspects such as more control over which threads run when, and lower costs of context switching, for example. Also, there are crates that allows you to use the green threading. Now we have defined threads in Rust. Let's explore how to use the thread-related API provided by standard library. Ooh, we're creating threads now. Oh, we can spawn it. We can spawn the thread. I like this part. This feels like zombie. You can just spawn them. To create a new thread, we'll call the thread spawn function. So we need to import the thread and import the duration. During. You guys like during? And create a thread. We put a closure implied. Thread spawn. And then we tell the spawn how do we want to spawn. What does the thread do? So for I in 1 to 10, a print line I number from the spawned thread. And then is it I? So I think I can do this. And then thread slip duration from millis1. So your slips for 1 millisecond. That's it? Oh, one thread? What does it do? Do we have in total we have one thread. And in this thread we sleep 1 millisecond for 10 times. 10 times? Okay, let's move on. For I in 1 to 5, implying that this is the main thread, and the thing above is the spawn thread. High number from the main thread. And then thread sleep duration from millis 1. Okay, so if we run this, what's gonna happen? I think the spawn thread and the main thread would be running at the same time, and the number from 1 to 10 and 1 to 5 are going to intertwine. Is it? Yeah. Wait, where did the 10 go? Where did 5? Where did the 5 go? Hold on. What's going on? My numbers magically disappeared. Oh, the new thread will be stopped when the main threads end, whether or not it has finished running. So main thread is like a mama. When mama dies, the baby just stops running. So it doesn't have a 10. And if we reverse the two, then we have the larger number. We have the thread below finish. And I realize Rust doesn't include this number. Okay. The close to thread sleep force a thread to stop its execution for a short duration, allowing different threads to run. The threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads. In this run, the main thread printed first, even though the print statement from the spawn thread appears first in code. And even though we told the spawn thread to print until I is 9, he only get to 5 before the main thread shut down. If you run this code and only see output from the main thread or don't see any overlap, we can increase the number range. So if we change back the number range, or I don't know, make it even bigger, both of them will stop at 50 or 49. Waiting for all threads to finish using join handles. Oh, the join! Welcome, Paul. When Mama dies, yeah, bet. Bambi flashbacks. Yes, that was a really old cartoon. That was really old. You're such a boomer. Bambi is so cute. Oh. I feel like when Mama dies, it's like a swear. Somehow, but anyway. Waiting for all threads to finish using the join handles. I guess this is gonna wait for the spawn thread to finish. If we add something like thread.join. Please don't kill Mama. Okay, I'll be mercy. I'll be nice. And kill the children first. The code not only stops the spawn thread prematurely most of the time due to the main thread ending, but also can guarantee that spawn thread will get it wrong at all. The reason is that there's no guarantee on the order which the thread's wrong. It doesn't even guarantee the spawn thread will run at all. We can fix the problem of spawn thread not getting to run or not getting to run completely by saving the return value into a variable. Oh! Let's save it into a variable. Let's save the baby. Turn out for a second, we're talking about my tree side. I've never seen that word before. We're reaching a level that I cannot comprehend. Handle. Okay. Oh, it knows it's a join handle. The thread returns a join handle. And at the end, we do handle.join, and because it returns a result, right? I think it returns a result. Otherwise, why do we use unwrap? Yeah, it returns a result. So we unwrap it. Unwrap. And now, we can have the children finish before we end the program. Yeah, the children get to finish. And the mama finished first. Calling join on handle blocks the thread currently running until the thread represented by the handle terminates. Calling join on the handle blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means that a thread is prevented from performing work or exiting. Because we have put the call to join after the main thread's for loop, you will have this output. Wait. The two threads continue alternating, but the main thread waits. The main thread waits because of the call to handle.join and does not end until the spawn thread is finished. So if we move this above the single main thread, what's gonna happen? Ooh! The spawn thread does its own business and finishes business before the main thread starts running. Konnichiwa! Ohayo! Ohayou gozaimasu. The main thread will wait for the spawn thread to finish and then run its for loop, so the output will not be interleaved anymore. So it's important where it is joining it. If it's before the main, it's gonna wait for the spawn thread to finish to start the main. And if the join is after the main, it's gonna interjoin. Using move closure with thread. The move closure is often used alongside thread spawn because it allows you to use data from one thread in another thread. Okay, what is the move keyword again? We can use the move keyword before the parameter list of a closure to force the closure to take ownership of the values it uses in the environment. This technique is especially useful when creating new threads in order to transfer ownership of values from one thread to another. We can use the move keyword before the parameter list of a closure to force the closure to take ownership of the value it uses. So we are taking the ownership of the value it uses. And here we have no arguments. We're not using any data from the main thread. To use the data from the main thread, the spawn thread closure must capture the value in it. So this is something that won't work, and we are going to figure out why it doesn't work. We have a vector, we have a handle, of a spawn thread that has nothing, and we are trying to use the vector in main. And why is it not okay? It says closure may outlive the current function, but it borrows v, which is owned by the current function. So the closure uses this v. You will capture v and make it part of closure's environment. And because the thread, the spawn thread, runs this closure in a new thread, we should be able to access v inside the new thread. But when we compile, we got an error. Rust infers how to capture v, and because println only needs a reference to v, the closure tries to borrow v. However, there's a problem. Rust can't tell how long the spawn thread will run, so it doesn't know if the reference to v will always be valid. I'm confused. What the heck? Rust can't tell how long the spawn thread will run, so it doesn't know if the reference to v will always be valid. So here we need a reference to v, and in a closure, Let me review what the remove does on chapter 13. Not the remove, but the move. What exactly does move do? If you want to force the closure to take ownership of the values it uses in environment, you can use the move keyword before the parameter list. This technique is mostly useful when passing a closure to a new thread to move that data so it's owned by the new thread. A bit? I don't remember much of this. A closure can capture the environment and access variable from the scope in which they are defined. So are we trying to capture it or not? We need to override this borrowing behavior to be moved instead of borrow. Every time you use a variable in a closure, that's not a parameter, it's captured from its scope. Here the parameter list is empty, but you use we, so we is captured. So closure used we and we is captured. We could be defined in a block, and the handle join could happen after the end of the block. Then the thread, if only borrows we, will still be running while we already got dropped. Oh, it's saying that we want the culture to have the ownership of we. So when the thread runs, the we will always exist. Oh, the spawn thread will own the closure we passed to it, and the closure will borrow or own each captured variable. Since the thread must not borrow local data, the closure must not borrow parse. And the move keyword forces ownership of all captured variables. Like instead of borrow, we want to own the variable. And to do that, we use move to capture it. To take the ownership of the we add a move keyword. Okay. Thank you for explaining. I think I got the smart gist of it. Thank you, Yuvan. Thank you, Frank. Okay. And see this example. Here it's saying vector equals to 1, 2, 3, and while the thread is running, we drop the we drop the we before the thread finishes running, and there will be a problem. And Rust doesn't allow it. There's a possibility the spawn thread will be immediately put in the background without running at all. The spawn thread has a reference to we inside, but the main thread immediately drops we using the drop function. Then, when the spawn thread starts to execute, we is no longer valid, so reference to it still is also invalid. Okay, so we use move in here, and it makes dropping it invalid because it's been moving into the thread. Adding move keyword to your closure path to a thread will never hurt. In cases where all variables are already captured by move, it doesn't make a difference. Oh, so usually we add a move in the closure, so it wouldn't cause more problem. Is that like that? What will happen to the code where the main thread code drop if we use a move closure? Will move fix the case? It wouldn't. So if we if we were still have this drop, if we have the drop in the main, it would say use of a moved value. We're being saved by Rust ownership. We got an arrow because Rust was being conservative and only borrowing V for the thread. The main thread, which means the main thread. Wait, what? By telling Rust to move the ownership of V to the spawn thread, we're guaranteeing Rust that the main thread wouldn't use V anymore. Okay, the ownership works. So it doesn't allow us to drop, and things will be happy ever after. I feel an example of a concurrency bug here can motivate understanding, but it's hard to write it in a simple way because Rust has the safeguard. So making a mistake is not allowed. It's not allowed in Rust. The only mistake you can make are compile time. Okay, I think I got most of it. Move on. Use a message passing to transfer data between threads. Oh, we're talking about inter-thread communication? I wrote C before, so I knew what is prevented by this. So C would allow you to drop something used by a spawn thread and give you runtime error. By the way, there's also a more advanced thread spawning API in the Create Crossbeam that allows spawn thread to capture local variables. It will make sure to join all threads before borrow data dies. Crossbeam. It's tools for concurrent programming. In the future, Rust ATS will get something like, what is ATS? Oh. Wait, something is in development? There's a proposal. The API I mentioned in the function is crossbeam scope, if anyone is wondering. There's a proposal for Rust standard library to get scope thread similar to crossbeam. It's already on nightly? Wow. It's a growing language. Okay. Inter-thread communication. Using message passing to transfer data between threads. One increasingly popular approach to ensure safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here is the idea in a slogan from the Go language documentation. Do not communicate by sharing memory. Instead, share memory by communicating. Is it saying like don't share the memory directly, but you can share your information through communication? One major tool Rust has for accomplishing message sending concurrency is the channel, a programming concept that Rust standard library provides as an implementation of. You can imagine a channel in programming as being like a channel of water, such as a stream or a river. If you put something like a rubber duck or a boat into a stream, it will travel downstream to the end of the waterway. A channel in programming has two halves, a transmitter and a receiver. Is this the producer-consumer problem? Hello, Angel. And hello, Ayumi-chan, welcome. Okay, so a channel has two halves, a transmitter and a receiver. This transmitter is the upstream location where you put your rubber ducks in the river, and receiver is where the rubber duck ends up downstream. One part of the code calls method on transmitter with the data you want to send, and another part checks the receiving end of varying messages. A channel is said to be closed if either the transmitter or the receiver is dropped. So we need two parts for the channel, a transmitter and a receiver, and they need to be both available. Here we will walk up to a program that has one thread to generate values and send them down a channel, and another thread that will receive the values and print them out. We'll be sending simple values between the threads using a channel to illustrate a feature. Once you are familiar with the technique, you can use channels to implement a chat system or a system where many threads perform parts of a calculation and send the parts to one thread that aggregates the result. Okay, let's create a channel. Use STD sync. What is MIPSI? Multiple producer, single consumer. P4Q. As threads run, they diverge in their worldview. So to communicate effectively, they must synchronize. Synchronize. How do they synchronize? We have a main function, and we have a transmitter, receiver equals to channel, and you cannot run it because it doesn't know the values we want to send over the channel. We create a new channel using the multiple producer single consumer channel. The Rust standard library implements channel means a channel can have multiple sending ends that produce value, but only one receiving end that can consume the value. Imagine multiple streams flowing together into one big river. Everything sent down any of the string will end up in one river at the end. We'll start with a single producer for now, but we'll add multiple producers when we get this example working. It returns a tuple, and we have the sender and the receiver. Let's move the transmitting end into a spawn thread and have it send one string so the spawn thread is communicating with the main thread. This is like putting a rubber duck in the river upstream or sending chat message from one thread to another. A channel is where they come together and synchronize their worldviews and exchange data. Oh. The communication channel. I saw this there. Then what does the sync keyword do? I guess I'm gonna see it in the later part of the chapter. So we have a kosher. And this is the variable that we're going to send. And in the sender, we send the value. Gotta import this. Thing only gets real once you send channels through a channel. Wait, you can send your channel through your channel? You can send yourself through it? That's not possible, right? Again, we're using the spawn to create a new thread and using the move to move the sender into closure. So the spawn thread owns the sender. The spawn thread needs to own the transmitting end of the channel to be able to send message through the channel. Okay, this is the transmitting or the sender. The transmitting end has a send method that takes the value we want to send. The send method returns a result, so we need to unwrap it. We get the value from receiving end of the channel. Here, let received equals to receiving end dot receive dot unwrap, and print line dot. Received. What do we have there? Oh, this is not received. Receive. Oh, we have a sender and we receive. Can I also print line something here? Sending. With Rust, you can do anything. Is that real? Yup. We send something in the spawn thread and receive it to the receiver. And the receiver has this receive or try receive, which will block the main thread execution and wait until a value is sent down the channel. Oh. So if we send nothing, this is not going to work. When the sending end of the channel closes, receive will return an arrow to signal that the normal values will be coming. The try receive doesn't block but will instead return a result immediately. An OK value holding a message if 1 is available, and the arrow value if there aren't any message at this time. Using try receive is useful if the thread has other work to do while waiting for messages. We could write a loop that calls try receive every so often, handles a message if 1 is available, and otherwise does other work for a little while until checking again. Okay. I can even conquer the world. So does the Rust developer own the world yet? When we run the code, we see a printing value. Yes, we did. Sending channels through channel is actually somewhat sensible to do. Imagine some worker thread. You can send it a task together with a sender for sending back the result. What? Really? A worker thread? What? Sending channels through channel. So, but the worker, wait. But the sender that is sending the sender are the two different things. Wait. It cannot send itself, but I imagine you can send the other sender. This is weird. This is weird. Channels and ownership transference. The ownership rules plays a vital role in message sending because they help you write safe concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership throughout your Rust programs. Let's do an experiment to show how channels and ownership work together to prevent problems. We'll try to use a wall value in the spawn thread after we have sent it down the channel. Okay, let's see why this doesn't work. Like some companies sending you a letter containing an empty envelope but sending stuff back. Oh, that makes sense. That makes sense. Even though I never sent back, but it's a great example. I always receive letters with like empty envelopes inside. That's an amazing analogy. Okay. What do we have here? We have a transmitter and a receiver. And in the thread, we send hi. And in received, we should receive hi. What's wrong with it? Oh, because we're trying to print it. But we have already sent it. Once the value has been sent to another thread, that thread could modify or drop it before we try to use the value again. Potentially, the other thread's modification could cause errors or unexpected results due to inconsistent or non-existent data. However, Rust gives us an error if we try to compile the code. Okay, so the Rust it's trying so hard to prevent it happening. So after we send the value to another thread, it's saying the value has been moved and you should not use it in case it has been edited. Okay. Nice job, Rust Mama. Our concurrency mistake has caused a compile time error the send function takes the ownership of the parameter, and when the value is removed, the receiver takes the ownership of it. This stops us from accidentally using value again after sending it. I feel like I'm gonna totally do that and let Rust yell at me. Sending multiple values and seeing the receiver waiting. I like to see people wait. How do we do that? How do we do that? So now we have a vector of things being sent. String from 9. I from the thread. And we're sending this whole thing. And we're not sending this whole thing. We're sending it one by one. Unwrap, thread, sleep, duration, from sections. So every time we send one value, we sleep. Whoa, whoa, whoa. This is values, and we need to import duration. Use std time duration. And what is the magic over here? You can just for received in receiver. And got each of the value. Oh, this is kind of cool. It sends each value and wait for 1 second to send another value. And on the receiver end, we receive one value every second. This is kind of cool. The spawn thread has a vector of string that we want to send to the main thread. We iterate over them, sending each individually, and pause between each by calling the sleep function. In the main thread, we're not calling the receive function explicitly anymore. We're treating the receiver in as an iterator. I was like, you can do that? And it looks like, yeah. The receiver can be an iterator. The main thread is wanting to receive values from the spawn thread. Creating multiple producer by cloning transmitter. So we can have multiple producers. Right now we only have one. We have one thread. And now we want to have multiple threads. And to do that, we need to clone the transmitter. So let tx1 equals to tx.clone. And here we have the first thread. And here we have the second thread. And we're using another transmitter. Transmitter. And we change the message up. More messages, massages for you. This time, before we create the first spawn thread, we call a clone on the sending end of the channel. This will give us a new sending handle we can pass to the first spawn thread. So we have two sending. What? Sending handle. We call them sending handle. There's so many names. Sending handle, sender, sending transmitter, what? Transmitting, and it's just so many different words for one thing. Each sending different message to the receiving end of the channel. So now if we run this, two threads are sending the message to the receiver end at the same time. So it's interleaving messages. I want to have some massages. Maybe some ear massages. Oh. You might see the values in another order, it depends on your system. This is what makes concurrency interesting as well as difficult. If you experiment with thread sleep, giving it various values in different threads, each run will be more non-deterministic and create different output each time. Okay, channels, not too hard. It's just two things talking to each other. One thing sending, other receiving. Let's look at different methods of concurrency. Shared state concurrency. Message passing is a fun way of handling concurrency, but it's not the only one. Consider this part of a slogan from the Go language. Documentation. Do not communicate by sharing memory. What would communicating by sharing memory look like? In addition, why would message passing enthusiast not use it and do the opposite instead? In a way, channels in any programming language are similar to single ownership, because once you transfer a value down a channel, you should no longer use that value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time. As you saw in chapter 15, where smart pointers made multiple ownership possible. Multiple ownership can add complexity because these different owners need managing. Rust type system and ownership rules greatly assist in getting this management correct. For an example, let's look at Mutex. We're looking at Mutex, one of the more common concurrency primitives for shared memory. It's finally Mutex! We're finally doing mutual exclusion. Using Mutex to allow access to data from one thread at a time. Mutex is an abbreviation for mutual exclusion, as in, a mutex allows only one thread to access some data at any given time. To access the data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex lock. The lock is a data structure that is part of the mutex that keeps track of who currently has exclusive access to the data. I never thought of mutex as a data structure. So it's like mutex.owner equals to this person and the other person can take it. I finally made it, I know. Therefore, the mutex is described as the guarding the data it holds while the locking system. Mutexes have a reputation for being difficult to use because you have to remember two rules. You must attempt to acquire the lock before using the data. Okay? And then, when you're done with your data, you must unlock the data so other threads can acquire the lock. For a real-world metaphor of Mutex, imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use the microphone. When they get the microphone, they can talk for as long as they want and then hand the microphone to the next panelist who requests to speak. If a panelist forgets to hand the microphone off when they're finished with it, no one else is able to speak. If management of the shared microphone goes wrong, the panel won't work as planned. Okay. So sharing microphone is like sharing Mutex. And my baby cat is here. Hello. My cat is so warm. It's sunny outside, and my cat has rinsed himself in the sunshine. So warm. Management of mutexes can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. However, thanks to Rust type system and ownership rules, you can get locking and unlocking wrong. What? What? You can't get it wrong? That is so protective. Rust is so protective. Okay. You like the spams that happens random with the camera? That happens because my cat is in the way. My cat is like pushing me everywhere. Whenever there's spams, you know my cat is here. Yeah, baby. Yeah. It's nice. Welcome, Burrow. Feed the cat? No, never. Okay, we're going to look at how to use Mutex. We can use the Mutex, import it from the sink, and then we have a Mutex value of 5. And in this block, m.block.unwrap num equals to 6. What is this? What is this? Cat having powerful force, did you? Cat is the one moving the character and Cyan is only doing the voice acting. Everything can be possible. As with many types, we create a mutex t using the associate function new. Okay. Why is the data at 5? To access the data inside the mutex, we use the lock method to acquire the lock. This call will block the current thread, so you can't do any work until it's our turn to have the lock. Looks like when this happens, the other people cannot lock the mutex, and 5 is the value in the mutex. The call to the lock will fail if another thread holding the lock panicked. Oh, so if another thread is already holding the lock, this will fail. So we've chosen to unwrap and have this thread panic if we are in that situation. Thus, the call to lock will fail if another thread holding the lock panicked. So the other thread panicked first, and our call to the lock will fail. So they panic together. What the heck? If another thread is holding the lock, it will wait for the other thread to finish. I'm so confused. This doesn't make sense. I mean, like if one thread is using a lock, is locking the mutex, then the other thread won't be accessing it. I feel like that's the main thing behind it. But what is this thing? If another thread holding the lock panicked, the call to lock will fail, and no one will be able to get the lock. And if that happens, we will make this thread panic too. What? The family panics together, stays together. Gosh. I don't want to be in a panic family. Only another thread panicking while holding the lock causes failure. The rationale is that the other thread might have left things in an inconsistent state due to the panic. Only another thread panicking while holding the lock causes failure. Okay. So if another thread messed up for some reason and other thread trying to call the lock will fail. Okay. After we have acquired the lock, we can treat the return value. Oh, this changed the value. It changed the value in the mutex. The type system ensures that we acquire a lock before using the value. We acquire a lock before using the value in it. So we must acquire a lock to be able to use the value. We need to acquire the lock to get a value. There's a crate called parking lot where it has another mutex implementation that does not get poisoned. Is parking lot a common system design question that has a concurrency? Is it related to concurrency? I don't know. It's just suddenly in my head. Instead of unwrapping, you can technically also ignore the arrow and access the value anyways. The docs show how that works. This thing is called Mutex Poisoning, and it's a bit controversial. You can poison a mutex. Oh. So instead of panicking, instead of unwrapping, you can access the value anyways. A mutex will poison itself if one of the mutex guards is dropping during a panic. Any future attempt to block mutex will return an arrow or panic. But if we ignore the panic, we can still use the value. Yes? But I feel like it has been polluted if we don't know why the previous thread panicked. I know it sounds dramatic. It sounds like we're in a game. We're in Minecraft or something and got poisoned. As you might expect, mutex T is a smart pointer. More accurately, the call to lock returns a smart pointer called mutex guard, wrapped in a lock result that we handled with the call to unwrap. The mutex guard smart pointer implements DWrap to point at our init data. The smart pointer also has a drop implementation that releases the lock automatically when mutex guard goes out of scope. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads because the lock release happens automatically. After dropping the lock, we can print the mutex value and see that we were able to change the inner integer to 6. Okay. If a thread panics while holding the lock, the data behind the lock is considered corrupted. The standard mutex decides to poison itself to prevent access to corrupted data. There's a book called Rostonomicon. So we cannot use the value if the mutex has been poisoned. Okay, let's implement. Let's actually try using it first. You can get the mutex guard out of the poison arrow if that's the case. I feel like it's all at once. Mutex. Function main. At m equals to mutex new 5, and let mutable num equals to this block unwrap, and then we set the number to equal to 6. And then we print line m equals to m. And do this. Oh, it wants some format. Question. Oh, it has a poison. That's a poison. It's not poison. And it has been changed to 6 after dropping the lock. Sharing a mutex between multiple threads. Now let's try to share our value between multiple threads using mutex. We'll spin up 10 threads and have them each increment the counter value by 1. So the counter goes from 0 to 10. Then the next example will have a compiler arrow, and we use that arrow to learn more about mutex and how Rust helps us to use it correctly. Okay, so we first have a counter that is a mutex, a new mutex of 0. Handles whack. For 10 times, we want to increment the mutex. That handle equals to thread from move posture, and we have let mutable num equals to counter.log.unwrap. We take the data in the mutex. Also use then the library thread. And we want to change the value of num, so it's counting every time we have a thread. We spawn a thread. And we push the current handle into a vector. And for handle in handles, handle.join.unwrap. So we're stopping all the threads here. And then result equals to the value inside the mutex. Wait. It's gonna show. Wait, it's not okay. Why is it not okay? It says move occurs because counter has type this, which does not implement the copy trait. The counter value was moved in previous iteration of the loop. Oh, it has been moved multiple times. Like it wants to move the counter multiple times, but it can't do it. Oh, so now we need to use rec_self. Cool. Everything's counting. We gave a value multiple owners by using the reference counting to create a reference counted value. We wrap the mutex in reference counting and clone the reference counting before moving ownership to the thread. Okay, so over here I have the reference counting. Let counter equals to reference counting clone counter I need to import it. Mutex. I think my wave is going a little crazy. What's happening? Oh, I have the caps on. I was like, what the heck? Counter started. Oh, the counter should start at 0. Hello, welcome. Oh, viral the show. Hello. Okay, the problem of it. What's the arrow? I feel like it's a different arrow from the example. This arrow is saying cannot be sent. This cannot be sent in between the threads safely. Read the whole arrow message. Oh. Oh. Nice tip. Nice tip. I forgot to import Mutex. Okay, now it's a different arrow, which is the same as the example. So the reference counting cannot be sent between threads safely. The trait send is not implemented. Reference counting. Of the mutex. Oh. So all this trying, all this time we spend, it comes to tell me that reference counting is not safe to share across thread. Why? When reference counting manages the reference count, it adds to the count for each call to clone, and subtracts from count when each clone is dropped, but it doesn't use any concurrency primitives to make sure the changes to the count can't be interrupted by another thread. This could lead to run counts, subtle bugs that could in turn lead to memory leaks or value being dropped before we're done with it. Oh, so we can't use this. Instead, we need to use this. What is this? I've never seen this. Arct? Arct? Automatic? Is an automatically reference counted type. Atomics are an additional kind of concurrency primitive that we won't cover in detail here. Atomics work like primitive types, but are safe to share across the thread. Hello, welcome. I'm trying to figure out how to let multiple threads to access mutex. Not automatic, atomic. Wait, there's no automatic? This is for atomic. Okay, I remember something like atomic operation a long time ago. but it's a primitive type that's safe to share across the thread. Okay, so it's not atomically referenced content type. Thank you. You might wonder then why all primitive types aren't atomic and why standard library types aren't implemented using atomically referenced content type by default. The reason is that the thread safety comes with a performance penalty. Okay, so only one concurrency we wanna use atomically referenced content type. It's automatic too, but reference counting is automatic as well. So we need to be atomic for concurrency. So if we just change the use line, I think atomic is not automatic, and we change the it's not AC, it's ARC. And here it's ARC clone. And then you can calculate the correct result. Oh, so smart. So smart. We did it! We come from 0 to 10. We can divide a calculation into independent parts, split those parts across threads, and use a mutex key to have each thread update the final result with its bug. Nice. Similarities between refcell, reference encoding, mutex, and atomic reference counting. You might have noticed counter is immutable, but we could get a mutable reference to the value inside it. This means mutex provides interior mutability. Oh, it is immutable, and we can change the stuff inside it. In the same way, we use refcell to allow us to mutate content inside the reference counting. We use mutex to mutate content inside automatically referenced counter. Another detail to note is that Rust can protect you from all kinds of logic error when you use mutex. So mutex comes with the risk of creating deadlocks. Those occur when an operation needs to lock two resources, and two threads have each other acquired one of the locks, causing them to wait for each other forever. If you are interested in deadlocks, try creating a Rust program that has a deadlock. So when we have two we need to lock two resources, and two threads have each acquired one of the locks. They have to wait for each other forever. Oh. We counted 1 to 10. When? We count from 0 to 9. Wait, what? What? There's more interesting abbreviation in Rust besides arc. For example, cow is probably my favorite. No chance to know what that means without looking it up. It's unrelated to cattle. What is cow? Rust cow. cow in std borrow. Cow is a very convenient enum. It means clone on write and lets you return a string size if you don't need a string. What does it do? I want to say that the other ones, last book seems intimidating. A clone on right smart pointer. You can enclose and provide immutable access to borrow data and clone the data lazily when mutation or ownership is required. We're throwing animals in our code. The name is funny. I think people should make a neko. I think that abbreviates to neko. So instead of cows, we can have a field of cats. That'd be nice. If I were to write a library, I'll do a neko. Okay, that is dialogue. Oh, it doesn't talk about async, looks like, but it talk about send and sync. Extensible concurrency with the sync and send trait. Interestingly, the Rust language has very few concurrency features. Although almost every concurrency feature we have talked about so far in this chapter has been part of the standard library, no language. The options for handling concurrency are not limited to a language or standard library. You can write your own concurrency features or use those written by others. However, two concurrency concepts are embedded in the language: the marker traits sync and send. Cyan's gonna write a library. I don't know. I haven't think about what to do after I finish this. Allowing transference of ownership between thread and send. Between threads with send. So when threads send stuff, it can transfer ownership. The send marker trait indicates that ownership of values of the type implementing send can be transferred between threads. The ownership of the values of the type implementing send. Okay? Almost every Rust type is send. But there are some exceptions, including referencing counting T. This cannot be sent, because if you clone a referencing counting value and try to transfer ownership of the clone to another thread, both threads might update the reference count at the same time. For this reason, reference counting is implemented for use in single-threaded situations where you don't want to pay the thread-safe performance penalty. Therefore, Rust type system and trace bounds ensure that you can never accidentally send an reference counting value across threads unsafely. When we try to do this, we got the arrow. Okay, any type composed entirely of send types is automatically marked as send as well. Almost all primitive types are send. So you can send all the primitive types without worrying it cannot be sent. Okay. Allowing access from multiple threads with sync. The sync marker trait. The sync marker trait indicates that it is safe for the type implementing sync to be referenced from multiple threads. In other words, any type T is sync. If an immutable reference to T is sent. The reference can be sent safely to another thread. Similar to send, primitive types are sync. And types composed entirely of types that are sync are also sync. It's like transitive. The types that only has sync is sync too. The small pointer reference counting is also not sync for same reasons that it's not sent. The reference cell type and the family of related cell type are not sync. Looks like all the like the immutable, wait, how do you call it? The stuff that deal with smart pointer, they don't do well in concurrency. The implementation of borrow checking that ref cell does at runtime is not thread safe. The smart pointer mutex is sync and can be used to share access with multiple threads. The smart pointer mutex is sync and can be used to share access with multiple threads. Okay, so mutex is sync. Ref cell and reference counting are not sync or send. It doesn't go to detail of it. It's pretty confusing to read already. Mitama, hello, ohayo. Implementing send and sync manually is unsafe because types that are made up of send and sync traits are automatically also send and sync. We don't have to implement those traits manually. As marker trait, they don't even have any method to implement. They're just useful for enforcing variants related to concurrency. Manually implementing these traits involve implementing unsafe Rust code. We'll talk about using unsafe Rust code in chapter 19. For now, the important information is that building new concurrent types not made out of send and sync parts require careful thought to uphold safety guarantees. The Rustonomicon has more information about these guarantees and how to uphold them. Okay? So you're saying, let's not do that? Let's not manually implement those traits and just use what we have, unless we want to write unsafe Rust code. Wow. I hope the final project is going to use some of this stuff. I don't know. Use some mutex and stuff. Okay, summary. Oh yeah, I was just talking about it, saying the project will use the concept in a realistic situation. And very little of how Rust handles concurrency is part of the language. Many concurrency solutions are implemented as crates. This evolved more quickly than the standard library, so be sure to search online for the current state-of-the-art crates to use in multi-threaded situation. You guys just mentioned that the Beam The crossbeam thing is getting into the standard library. Yeah. Astronomical. Yeah, that's the word, right? You guys read Astronomical? How many books do you have to read to be proficient in Rust? There's so many stuff. Oh, it says, warning, this book is incomplete. There's an issue tracker. Rust Learn Nomical. The dark arts of advanced and unsafe Rust programming, nicknamed the Nomical. What am I getting into? What am I getting into? 1. The Rust book. 2. The Rustonomical. What the heck am I watching? I wanna know what the heck am I doing? I feel like I'm doing dark arts. I feel like half of the people here has no idea what I'm doing, and the other half understand everything that I'm doing, and I am immersed. I'm being poisoned in a good way. I'm too deep to quit. I'm too deep to quit. Rustonomical is very optional. Rust for rustaceans? What? So there's something that's even harder. I'll consider getting a job in assembly programming. It's actually not that hard, right? I don't know. List of Rust books. Starter books, advanced book. Rust patterns. Oh my god. There's a really masculine crab in the O'Reilly. I don't know why books in O'Reilly has like so many different animals that I don't recognize. It makes me feel so stupid to not know the animals on that book, on those O'Reilly books. There's a freaking book on hands-on concurrency with Rust. Hands-on functional programming in Rust. 0 to production in Rust. And this crab is freaking carrying a skull. This is scary. Scary fun. Black Hat Rust. I need to stop watching this. I need to become a useful member of the society. No, come back. Let's do the dark magic together. I just read Rustonomical chapters which Google lists me to. How do I keep learning? I honestly do not know. How do I keep learning? You guys first struggle and then feel fun, or you guys never struggle? I felt struggle. Initially there wasn't much struggle. Now we get to Mutex. We get to spot pointers. I felt a little struggle. There's a book called Why Rust? And there's so many different kinds of ropes on the cover. There's too many books. Welcome, Hafnia. This is the end of introduction chapter, and now we'll start the real deal. I'll be able to do the real deal. I don't know if I'll be able to do the real deal. I've been writing Rust for years and never read the Rustonomical or use unsafe, so don't worry about it. That kind of reassures me. Okay, so we have done the concurrency, the fearless concurrency of Rust today. I struggle so much, but thank you guys for helping as always. It's been some struggle, but it's been some fun too. It's nice to remember more of the concurrency concepts. And maybe one day we'll do a chat room. We'll program a chat room in Rust and feel fearless. Hello, Facetitious, welcome. So, any plans on how to use the knowledge? I don't know yet. I don't know yet. I felt like writing something. Last time somebody recommended us a playground. Maybe we could. To the playground. I will be writing raw study material for a community. I hope, like, I don't know, after 3 years of this, I can make some Rust video. Don't let this knowledge rust, or you'll forgot how to rust. That is so chill. So far, we're planning on Neko library. What do we do with that library? When you guys learn a new language, how do you decide what programs to write? There's a video for Rust project idea for beginners. CLI application. After 3 years, I hope your skill haven't gone rusty. It's Rust called Rust because some people are going to get rusty. No, I don't think I can design a language anytime soon. Okay. I hope I got time to review this, and next time we'll be doing some object-oriented programming features of Rust. We have done pattern and matching before, and so maybe we'll do chapter 17 and chapter 19. Chapter 19 feels so big though. Or can we just skip chapter 19 because it feels like I'm not going to use unsafe Rust? Unsafe Rust. How do I feel after the basics? I feel I'm too deep in a rabbit hole. And I hope one day, or maybe next week, or maybe next week, we can build this web server and call ourselves graduated from Rust. Or the graduation is just a beginning. How do you decide what to do after learning a new language? See if you can contribute to open source projects, find some free code challenges, see if there's any ideas that interest you. really want to use some time to contribute to open source project. Maybe I should search up some project and resolve their issue. Is that how people get into open source projects? Unsafe routes is a vital part of language, even if you are not going to use it. You should still know something about it. Okay, I'll go over it. Then. For instance, I got into scripting some stuff in Python for CTF and just for automating some small text on my regular computer. CTF sounds fun. Alright, thank you for coming to the stream today. It is really fun. It's really fun today to learn about concurrency, to be reminded of mutex and dialogues. And yeah, next time let's look at object-oriented programming in Rust. Just found your channel and not gonna lie, I'm kind of mad. I found it just now. Your content is just what I was looking for. Thank you, Fastidious. Hope to see you next stream. Don't be too mad. I feel like people found my channel and they feel really happy that VTuber is doing some technical stuff. But I still have a very long way to go. I feel like I really wanna be somebody who's good at coding and I'm trying to spend more time on it, but I still have a long way to go. But it's nice that we have a community, so you guys can join Discord and many amazing people there sharing fun stuff. You can go onto your forums and try to sort out other people's code or answer questions. That's another thing I did a lot. Research questions other people have. I'm trying to answer questions on Stack Overflow. Being pretty fun. Anyways, thank you guys for coming. I got to grab some water. Today I ate some Pockies. I ate them like real cookies. I grabbed a batch of them and stuffed them in my mouth. Take a big bite. It feels like I'm eating cookies. It's really fun. Anyways, I'm gonna go. Have a good week. I'll see you guys on Friday, right? On Friday. Or Minecraft, if you wanna play Minecraft. Yep. Alright. Good night. Bye-bye. Thank you, you fun. Thank you, Ovalo. Thank you, Fastidious. Thank you, Havnia. Bye-bye. Thank you, Portia. Thank you, Zue. Bye-bye. Thank you, Wolfie. Thank you, Batomi. Thank you, Furrow. Thank you, Dragon. Thank you, Black Swan. Thank you, Arrow. Hello, and thank you. Bye-bye.